Hello guys, my name is Ruizhe Chen. I'm an undergraduate student studying at uiuc and majoring in actuarial science. This semester I'm taking a course about linear algebra, and I've done a research project about that course. My project is about the Lee-Cutter model for forecasting. And the Lee-Cutter model is widely used by a lot of actuaries for forecasting mortalities, and it is developed by Lee and Cutter in 1992. Today I'm going to give you guys a very brief introduction about the Lee-Cutter model, and I'm going to demonstrate some very basic ways of constructing the components of the model, because it's related to the linear algebra, so it's not going to be very technical, it's not going to be very hard or very difficult, just very brief introduction about it. Let's see. The Lee-Cutter model can be used for a lot of purposes, like from forecasting of mortality reduction factors to the assessment of retirement income adequacy. And the common assumption under this model is that the dynamics of death rates over time are driven by a single time varying parameter, the mortality index, and the mortality forecast relies on the extrapolation of this index. And the data that I'm going to show you guys is from the Human Mortality Database run by UC Berkeley and the Max Planck Institute for Demographic Research. And this data is the mortality data for USA from 1933 to 2010. And let me briefly introduce the model itself. Right? I will write it down. The Lee-Cutter model is mathematically log n of mxt equals to ax plus bx times kt plus an arrow term, which is x t. This one is arrow term, which captures the parameter set is not be able to capture by the model. First, about this term. This one is the logarithmically transformed age-specific central rate of death. This one is central rate of death, but it is logarithmically transformed, which means this one is actually a matrix. What I mean by saying that it is logarithmically transformed is we take the natural log of all the elements of the matrix, and all the elements of this matrix is from the mortality data. I have opened the website for the mortality data. You can see it. Not very clear, right? This column says mx. This one is mx, and mx is the central mortality rate. This is from year 1933. This 0, like in year 1933, from age 0 to age, I think here is to age 110 plus. So we have specific central rate of death for each age from 0 to 109, but for age over 109 we have only estimated combined death rate for age 110 and plus. But that's the best we can do. And here I'm going to show you guys. Let me see. And the AX part. AX is also a matrix, but it is this matrix is, we get this matrix by times a vector a vector AX by a vector of elements 1, which has the same number of elements as AX, the transpose of this vector. So we get a square matrix of AX, right? And the elements of AX are the arithmetic mean of the columns of this log n mxt, which means, like, let me show you the L n mxt first. This matrix will looks like the log n of m0 1933, log n m1 1933, and to log n m110 plus 1933. This columns means the logarithmic of the central death of rate at age 0 at 1933 to age 110 plus of at year 1933. And the second column is logarithmic of m0 1934, log of m1 1934 to log of m110 plus 1934. So this column is 1 year later than the first column, and we can go on until the log n of m0 210 and to log n of m111 plus 210. Yeah, this is a matrix of it. And what I mean by the vector AX is A0, A1 until A1 plus, and each, like, A0 is the arithmetic mean of this row, or the arithmetic mean of all the elements on this row of the in year 19 of age 0 through the year from 1933 to year 2010. And A1 is arithmetic mean of the central death rate at year 1 from the year 1933 to year 2010, like this row, yeah, until the central death rate as arithmetic mean of central death rate at year 110 plus. So that is the vector AX, and we get the matrix AX by timing it, multiplying AX by a vector transpose. The vector's elements are 1 and has the same number of elements as AX, and we get a square matrix AX. And now we get 2 elements of this Lee-Carter model. First one and second one, and we are trying to get this one. This one is a little bit difficult to get, and it's kind of beyond the scope of the course I'm taking. But as my instructor told me, like, to get this term, we applied, it's called a singular value decomposition, which is known as SVD, to the matrix log n mxt minus ax, which we got from here. We can got all the these two matrices, and we apply the SVD to this matrix, and that is the first step. Be careful that we have to set bx to unity and set kt to 0, which means we force the sum of all the elements in bx to 1 and the sum of all the elements of kt to 0. And after applying the SVD, we will re-estimate the time series of kt by solving for kt such that dt equals to sigma x of e to the ax plus bx kt times nxt. The dt is a total number of deaths in time t, and nxt is the exposure to risk of hx in time t. And then we can get kt. The kt is projected into future using ARIMA. ARIMA is another techniques to in linear algebra that I'm not going to talk about it because it's very technical and very difficult. Time series method, it's called ARIMA time series method, and will yield the mortality matrix. Because of the linearity of the kt, it is generally modeled as a random walk with trend, and we can get life expectancy and other life tables by calculating from this matrix, and will yield the regular mortality rates. This is briefly the introduction of the Lee-Carter model, and the mortality rate forecasting is very valuable for societies in making pension plans, and it is especially important in wealthy countries with a high portion of aged people, because of aged people are more expensive in terms of the pensions. And thanks for watching this video, and hope you guys enjoyed it. My name is Ray.